So in this case, we last left off discussing different leaving groups, and we'll talk again about the features that make a good leaving group. So the leaving group must accept negative charge easily and stabilize negative charge, but not too strongly. Another main feature is that the leaving group must be bonded to an sp3 carbon for SN1, SN2, E1, and E2 reactions. So in general, your leaving group needs to be attached to an sp3 carbon for you to observe appreciable reactivity through any of these reactions that we're going to talk about momentarily. In general, good leaving groups are weak bases that can stabilize and delocalize electron density. In general, good leaving groups, which we'll abbreviate as LG, are bad nucleophiles. Okay. So now that we have that idea sort of presented, let's talk about preparing a leaving group. So there are a variety of methods that we can use to convert a poor leaving group, such as an alcohol, into a more effective leaving group. This is commonly done via substitution or activation of our leaving group via formation of a covalent bond or via a Lewis acid. In both cases, we have in turn replaced our relatively poor leaving group of an alcohol with a much more effective leaving group. So would anyone like to comment, why is this functionality, why is this motif a better leaving group? What's the main feature of this motif?
Resonance?
Yep, exactly right. We have a stabilized, and more specifically, a resonance stabilized anion. Exactly right. Perfect, perfect. So treatment with thionyl chloride allows us to generate an alkyl chloride from our alcohol. Note this occurs with inversion. Does everyone see how our stereochemistry at this stereocenter has flipped? This is really important to be conscientious of. Activation followed by SN2 reaction. So in this case, our chloride is displacing this leaving group. This process occurs with inversion of stereochemistry. Does that idea make sense to everyone? So this is how we can prepare chlorides and bromides from alcohols in a stereospecific manner. Okay, so let's keep going with this. And let's talk a little bit about the solvent. So for SN2 reactions, a higher energy nucleophile generally results in a faster reaction rate. Okay. Now, thinking about our two types of solvents, we're going to look at polar protic and polar aprodic solvents. So polar protic solvents that can donate hydrogen bonds slow SN2 reactions by stabilizing the nucleophile. So if we have our nucleophile with its lone pair, hydrogen bonding protic solvents, such as for example, an alcohol solvent, are able to stabilize our nucleophile via hydrogen bond, and in turn, our nucleophile is less reactive. Does that make sense to everyone? Another way that we can think about this is that energy is now required to break interactions between the reactant nucleophile and the solvent. Comparatively, polar aprotic solvents form weaker interactions with our substrate nucleophile and permit faster SN2 reactions. So that's why SN2 reactions are typically run in polar aprotic solvents. So you don't end up reducing the reactivity of your nucleophile. So as we can see, we have some relative reaction rates for a substitution reaction in different solvents. Does everyone notice how our protic solvents have a substantially slower reaction rate? Does everyone notice that? Does everyone see how if we compare our protic solvents to our aprotic solvents, we see a substantial difference in reactivity and the rate of SN2 reaction. HMPA is a bit of a special case, hexamethylphosphoramide. HMPA serves as an activator because it sequesters cations. You can also see these kinds of additive effects and substantial acceleration of reaction rates through using quote unquote crown ethers. In both cases, this solvent is pretty unique in that it's particularly effective at sequestering and sort of interacting with the cation that's often floating around in solution. And because we have a more isolated anion, the anion is less stabilized by the interactions with the cation, and in turn, we end up with a slightly more reactive anion when we use HMPA as our solvent. HMPA can also produce modifications in selectivity if chelation is influencing the outcome of the reaction. Just something to note. Anyway, so a few other things that I'd want you to pay attention to are you should be able to recognize the common polar protic solvents and the polar aprotic. So the main polar protic solvents are going to be your alcohols, water, and acetic acid. These are the common polar protic solvents that you'll see. While the aprotic solvents would be tetrahydrofuran, acetone, dimethylformamide, acetonitrile, and dimethyl sulfoxide. These are all pretty common solvents that you'll utilize for SN1 and SN2 reactions. Does this idea of solvent effects make sense? We're going to look into this idea of solvent effects from the perspective of reaction energy diagrams. Okay, when we think about polar protic solvents can interact with nucleophiles and electrophiles, and they have a hydrogen that can undergo hydrogen-like bonding with the nucleophile. This in turn spreads out the electron charge over a larger volume and stabilizes and weakens our nucleophile. So these hydrogen bonding interactions stabilize our nucleophile and in turn reduce the rate of SN2 reaction. If we think about polar aprotic solvents, they cannot undergo hydrogen-like bonding, and because we're not delocalizing our electron density or stabilizing any lone pairs on our nucleophile, we end up with a much more reactive nucleophile as our charge is much more localized and our nucleophile is overall less stable in an aprotic solvent. Okay, so let's now look at the reaction coordinate, and we're going to look at the effect of modifications of our substrate, nucleophile, and solvent through this reaction coordinate. Okay, so there are a few main features that I want you to note for this SN2 reaction. First, it occurs in a single concerted step. right? There's just a single concerted step. The second feature that I want you to keep in mind, that I want you to be cognizant of, the nucleophile and the reactant are typically higher energy than the product leaving group and product molecule. Okay, so what will we call this reaction? Exergonic or endergonic? Exergonic or endergonic? Yep, it's an exergonic reaction. We have a delta G of reaction of less than 0. Okay. And a critical feature that I want us to pay attention to is this activation energy. And the activation energy depends on the nucleophile and reactant energy, right? So if the reactants or nucleophile are higher or lower in energy, that directly impacts our activation energy. Now, we're going to talk about these effects in detail, but first we notice sort of generally that the activation energy increases as the substrate substitution increases. Further, good leaving groups result in a lower activation energy, and the product energy depends on the leaving group. Okay, so with this initial view of this energy diagram for the SN2 reaction, let's talk about unpacking the effect of reaction conditions on the SN2 reaction coordinate. So first, let's talk a little bit about substrate hindrance. So first, as substrate hindrance increases, activation energy increases and reaction rate decreases. So remember, when we talked about the reaction rate, primary was faster than secondary, which is way faster than tertiary. You don't typically see reaction of tertiary substrates via the SN2 mechanism. So let's look at the two main points on this curve. We have our reactants, we have our transition state, and we have our product. Okay, we're not going to worry too much about our reactants, but let's just do a side-by-side comparison. So we have this primary. So we have this primary alkyl chloride. And we have a secondary alkyl chloride. Okay. So in terms of steric and torsional interactions, yes, there is going to be a small difference in the energy of each of our two starting materials. So let's add that to our diagram. So our primary substrate will have slightly fewer steric and torsional interactions that raise the energy of our system. Okay, so we'll have it somewhere around here. Now, let's look at our transition state. And this transition state is really important to consider. So in the transition state for the SN2 reaction, we are simultaneously forming our bond to the nucleophile and breaking our bond to the leaving group, right? Now, remember how, as we discussed last time, this transition state is very sensitive to this transition state is very sensitive to sterics. So, comparatively, so we're looking at our primary reaction coordinate. So here's what our primary reaction coordinate looks like, and we have this requisite activation energy. Okay, now, if we compare that to our secondary, if we compare that to our secondary substrate, what is the main difference when we look at the transition state for our secondary substrate? What has changed? What is the main difference when we look at our secondary substrate? What has changed? Our hindered substrate So yes, we conclude that it has a higher activation energy. As what's occurring in the transition state. So if we take a look at this transition state, is this transition state more or less congested? Do we see more or less repulsive interactions in this transition state for our secondary versus primary? Which of these substrates experiences more congestion as part of its transition state? As we see looking at the secondary substrate, we have this additional methyl group that increases the amount of steric interactions and destabilizing repulsive interactions in this transition state. And as a result, the transition state for the more substituted substrate is higher in energy. So the hindered substrate has a higher activation energy as the transition state is destabilized by steric interactions. Does that make sense to everyone? And that is why as we increase the substitution of our substrate, we end up with a greater activation energy as the transition state is higher in energy because it experiences more destabilizing interactions. Does that idea make sense to everyone? Hindered substrates have slower rates of SN2 reaction. The transition state is destabilized by steric repulsions, and as a result, when the more hindered your substrate, the slower the rate of reaction. Does that idea make sense to everyone? Do these pictures with the transition states drawn help you see why the hindered substrate has a greater activation energy and a higher energy transition state? Okay, perfect. So this explains the observed trend of reactivity of primary, secondary, way greater than tertiary. This also explains why bulky nucleophiles have slow or negligible reaction rates. Why would that be? Looking at the transition state, we care about the hindrance of our substrate and what else? What else is participating in this reaction? Besides our substrate, what else can engage? What else is present in this transition state? So we talked about hindrance on our substrate, but does the nucleophile's steric bulk impact this reaction? Does the nucleophile play a role in this transition state? Yes, clearly. And the more hindered your nucleophile is, the more congested and more steric repulsions you see in your transition state, and the higher the energy of your transition state, and the slower your reaction rate. SN2 reactions hate steric bulk and steric congestion. Does that idea make sense to everyone? You should be able to draw these energy diagrams just like I've drawn here on an exam, because I really feel like they help you rationalize and understand these trends in reactivity in a more quantitative way. Okay, let's talk about this next effect. As nucleophile energy increases, the activation energy decreases and the reaction rate increases. Okay, so let's line up our premises here. So we know that a good nucleophile is high in energy. Okay, So if we compare a good nucleophile to a poor nucleophile, we notice that the good nucleophile is higher in energy. So if we look at our activation energy, we notice something pretty interesting. Which of these reactions, the reaction with the good nucleophile or the poor nucleophile, which one of these reactions has the lower activation energy? The good nucleophile. The good nucleophile is higher in energy, and as a result, the activation energy is lower, and the rate of reaction is faster. Does that make sense to everyone? And barring differences in steric hindrance, the transition state will have roughly the same energy for both of these pathways. So the main thing I want you to keep in mind is that good nucleophiles are high in energy and are less stable than poor nucleophiles. That's also the reason why the SN2 reaction very rarely will go in reverse in an appreciable amount, because the activation energy for our reverse reaction is so large. Does everyone see how the reverse reaction has a pretty large activation barrier compared to our forward reaction? And this difference in activation energy is based on the difference in energy between our nucleophile and our leaving group. And usually we set up our SN2 reaction so our nucleophile is higher in energy, so it can kick out our leaving group, and our leaving group is set up so it's not very reactive. It's pretty stable. Does that idea make sense? Does this idea make sense for nucleophile strength? Okay, so let's talk next about the effect of the leaving group. So if we think about the leaving group, so if we think about our transition state here, so if we have a good leaving group, our activation energy is lower, because in our transition state where we're forming our bond with the nucleophile and breaking our bond with the leaving group, this carbon leaving group bond is easier to break. It's easier for you to kick out your leaving group. And if we think a little bit about this exergonic reaction, what does our transition state typically resemble in an exergonic reaction? So for our exergonic reaction, does our transition state typically resemble our reactants or products? So for an exergonic reaction, our transition state typically resembles our reactants, species closer in energy to the transition state. Okay, so if we have a good leaving group, it's easier for us to break this carbon leaving group bond. It's easier for us to dissociate the leaving group. And as a result, we have a lower activation energy. If we have a poor leaving group, it is difficult to dissociate the leaving group. And the transition state in turn is higher in energy. Additionally, a poor leaving group is higher in energy. Does that idea make sense to everyone? Is everyone comfortable with these concepts so far? Okay, let's now talk about solvent effects. So polar aprodic solvents stabilize the nucleophile, resulting in a larger activation energy and a slower reaction rate. So a aprodic solvent, we have a lower energy nucleophile. However, if we have the same nucleophile for both of these pathways, because we're going through the same nucleophile, the transition state is roughly identical for both of these reaction pathways. The transition state is identical for both pathways. As a result, when we use a aprodic solvent, because the transition state energy does not change substantially between these two pathways when we change our solvent, which of these pathways has the lower activation energy? Which of these pathways has the lower activation energy? The pathway in the aprodic solvent or the pathway in the prodic solvent? Polar prodic or polar aprodic? Aprodic, exactly right. So the nucleophile in polar aprodic solvents is less stable and higher in energy. As the transition state energy is identical in both pathways, the activation energy for the polar aprodic pathway is lower. Does that idea make sense to everyone? By stabilizing our nucleophile, we actually end up raising our activation energy. Okay, so let's keep going with this. And let's look at an example. So in this case, we're asked to draw a reaction coordinate comparing the following two reactions. So when you look at these pairs of reactions, it's important to think to yourself, what is different? And let's just take a look at this over a minute, and I'd like you to tell me what is different. What is different between these two reaction pathways? So we have students typing the solvent, exactly right, exactly right. So let's classify our solvents. So CH3CN, otherwise known as acetonitrile. My question to you is acetonitrile protic or aprotic? So looking at acetonitrile, CH3CN, is that protic or aprotic? Can that solvent hydrogen bond or not? It's aprotic, exactly right. So in the top reaction pathway, we have a polar aprotic solvent. Well, in the bottom reaction pathway, we have a polar protic solvent. So then, if we're drawing our reaction coordinates, so I'll label this top pathway 1 and the bottom pathway 2 in red. So then, let's draw our reaction pathways. So starting off, what is the critical distinction between pathway 1, which is dealing with an aprotic solvent, versus pathway 2 that deals with a protic solvent? What is the main difference for an SN2 reaction when we compare aprotic and protic solvents? What do we need to reflect in our reaction coordinate? What changes? What's the critical difference between aprotic and protic solvents? What do these solvents affect? What do we care about in this coordinate? What's the main distinction between an aprotic and protic solvent? What do these solvents affect? Yes, they affect our activation energy, but how? What are they directly interacting with? What are our solvents interacting with? What are they affecting? Could you elaborate? What do you mean by substrate? What do the solvents affect, stabilize, or destabilize? Or to ask this another way, in example 2, what species can hydrogen bond with my solvent? What species can hydrogen bond with my solvent? My nucleophile or my substrate? What can hydrogen bond here? Nucleophile or substrate? Which one? What does everyone think? Let's really focus on this example. Which of these two species? So we have our substrate and our nucleophile. Which of these species can interact with the solvent via hydrogen bonding? The nucleophile, exactly right. So when we compare aprotic to protic solvents, we are looking at the nucleophile energy and stability. And just as a reminder, polar protic solvents stabilize the nucleophile. So for example, if we have our acetate can participate in hydrogen bonding, with our acetic acid molecules, which is our solvent. So polar protic solvents stabilize the nucleophile. So then our aprotic system will be higher in energy. So aprotic will be higher in energy because our nucleophile is not stabilized by our solvent. Okay, so the pathway will proceed. We'll go through our transition state. I always like to draw things out since it helps me notice potential patterns. Okay, so here's the reaction pathway for an aprodic system. For our protic system, where should I draw my reactants? Where should I draw my reactants? Should I draw them higher or lower in energy? Higher or lower in energy? Based on this discussion, when we talked about protic solvents, they stabilize our nucleophile. So should I draw my reactants for my protic solvent system higher or lower in energy? Lower, right? So this pathway will be for our protic solvents. Now, you may say, why are we focusing on this so much? Well, the reason for that is this pathway that we're looking at is only one of the possible pathways these substrates can react through. So it's important to understand the effects when you change your conditions, because if you aren't careful, you can actually change the entire mechanistic pathway the reaction is proceeding through. Okay. Okay, so our transition states are roughly similar. The solvent doesn't play too much of an effect in this transition state for our SN2 reaction. So, does this make sense? How to draw a reaction coordinate and how to identify the major difference between our two pathways. And as we can see very clearly, the activation energy for our protic solvent pathway is greater than the activation energy for our aprotic solvent pathway. So if you want a fast reaction, you choose to use an aprotic solvent. Yes, I'd like you to draw out the structures, just as proper form. Especially if you need to look at the structures to make a major point. Does this example make sense now that we've gone through it together? Does this kind of analysis make sense? Okay, so let's look at this next example. And let's try to think, what is different? What is different? What is different between these two reaction sets? What is different? So we have someone focusing in on the fact we have sulfur. What do we call these species? What do we call these species? The nucleophile. Yep, so we have different nucleophiles. Okay. Now, I'd like you to tell me which of these two nucleophiles is better? Which of these nucleophiles is the stronger nucleophile? Acetate or ethane thiol anion? Which one is the better nucleophile? You can go to your table, just to help jog everyone's memories. Which of these nucleophiles places our electron density on a polarizable atom, and which of these nucleophiles has a relatively localized charge? Which of these nucleophiles is better? Remember when I talked about nucleophile strength? What's one thing that I told you is a hallmark of a really strong nucleophile? Which of these nucleophiles is better, one or two? What do we think? So we have some students commenting that they think two, this sulfur-centered nucleophile, is stronger. What does the rest of the class think? Let's try to get some discussion here, as this is a really important point. Does everyone agree or disagree? So we have tentatively that we think this second nucleophile is the stronger nucleophile. So we have students presenting arguments. The charge is relatively localized. Sulfur is a large atom. It's relatively polarizable. All of those explanations exactly correct. Yep. So with the second example, we have a stronger nucleophile. Okay. So then, the difference between these two reaction pathways is our nucleophile. So if we have a stronger nucleophile in the second pathway, is a stronger nucleophile higher or lower in energy? Is a stronger nucleophile higher or lower in energy? Stronger nucleophile, more reactive. What does that tell us? Higher or lower in energy? Higher in energy, exactly right. Okay, perfect. So now that we have this set up, let's draw out our pathways. So pathway 1, we have a bad nucleophile. In pathway 2, we have a good nucleophile, which means high energy. Okay. So then let's just draw pathway 1 as our reference. So we have our substrate, we have our nucleophile. We go through an activation energy. Oh, let's not draw it that large. Let me move this down so we have a little more space. There we go. Okay, and we have our transition state. Okay, perfect. Now, if we have a good nucleophile, should I draw my reactants higher or lower in energy? Should I draw my reactants higher or lower in energy? What does everyone think? If I have a higher energy nucleophile, should I draw my reactants higher or lower in energy? Higher, yep. Okay, we have our substrate. We have our better nucleophile. It's higher in energy. We go through a pretty similar reaction pathway, except our transition state is going to be different because we have a different nucleophile, obviously. And one thing that we can clearly see is that the activation energy for pathway 2 is less than the activation energy for pathway 1. So better nucleophile, higher in energy, lower activation energy, faster rate of reaction. Does that make sense to everyone? Do these examples make sense to everyone so far? Okay. So what I'd like us to do now is I'd like us to try and draw a reaction coordinate, and I'd like us to try and compare the following two reactions. Let's try to compare the following two reactions. So I'd like us to take about 3 to 5 minutes and first compare these two reactions and then draw a reaction coordinate for these two reactions. So I'm just going to zoom out a little bit to give students a little bit more space. Oops, one moment. Here we go. And I'd like us to try to view this reaction and set of reactions, and I'd like to see students draw a reaction coordinate in the spaces provided below and on the right on our class whiteboard, just to make sure that you're comfortable identifying differences between pairs of reactions, identifying the faster or more favorable reaction, and also drawing reaction coordinates. So I'd like you to draw a reaction coordinate comparing these two reactions, just like we did together in these earlier two examples. Don't be shy to share your thought process as you work through this problem, and especially try to note what is different between these two reactions. What is the difference, and how does that difference directly impact your reaction rate and overall favorability of these two reactions? So let's start working on these examples, and then we'll come together as a group to discuss in about 4 minutes. And don't be shy to share your responses using the annotate tool. So we see a student drawing out the proposed mechanism. Yes, this is in fact an SN2 reaction. Yep. But let's talk a little bit about the reaction coordinate. Now that we've recognized this is an SN2 reaction, what is the main difference between these two reactions? What is the main difference? Let's really focus in on that, as that's critical to drawing the reaction coordinate. So we say the carbon, what's different? So we have an extra carbon, yeah, and what does that impact? So if we compare these substrates, what would we call this first substrate? What would we call this first substrate? What type of substrate is this? Primary, secondary, tertiary, what do we think? Primary, right? And the second substrate, primary, secondary, or tertiary? Secondary, okay. So then we clearly have a difference in our substrate, right? So how does that impact our reaction coordinate? I'd like us to draw a reaction coordinate showing both of these pathways, and I'd like you to show the difference between these two pathways. If we change the hindrance around our substrate, what is very sensitive to steric hindrance? What is very sensitive towards substrate substitution? What changes? The activation energy, yes. So would you like to try and draw that? Would you be able to try and draw that in the space below? So we have some students mentioning that they think the second reaction will have a higher activation energy because our substrate is bulkier and has a greater amount of steric hindrance. Well, you're on the right track for that. Let's try and let's take what we've seen. Let's try to take what we've seen in the previous examples, and would anyone like to draw a reaction coordinate? I'll even draw the baseline part. So we have energy as a function of reaction progress, and I'd like to see pathway 1 and 2 drawn into this graph, just to make sure you're able to link sort of differences in reactions to differences in reaction coordinate. So we have this idea that the second reaction has a higher activation energy because the substrate's bulkier. Okay, so taking that idea, how would we convey that in our reaction coordinate? And there's plenty of space, so if you want to draw your coordinate off to the side, I've also left a blank template. No problem, no problem. So let's try to get a proposed reaction coordinate, and the class can contribute. There are three main parts for the reaction coordinate: your starting material, your transition state, and your products. As long as you have those placed and correctly labeled, you're more than okay. So the main thing that's different, as we were talking about from the primary versus secondary substrate, is the activation energy. So let's start there. Let's draw our two transition states and let's sort of draw them respecting their relative energies. So would someone like to take an attempt at drawing these two reactions, just starting out with the transition state? So just draw the two transition states and identify which one would be higher or lower in energy. Okay, and what about pathway 1? Okay. So we're starting to develop these ideas. So let me convey what the students have shared, and let's talk through this example. So let me zoom in a little bit and let's talk about this example together. You have the key points down. It's just important to make sure your presentation is as clean as possible in terms of how you've organized these parts. So the way that I like to set up my reaction coordinates is, first I like to think about my substrate, my starting material. In other words, I like to think about my reactants, then I look at my transition state, and then I look at my products. Okay? So I'm going to label pathway 2 in red, just so that way it's clear. Okay, so pathway 1 and 2, they're going to be about the same energy in the reactant side. For our transition state, as we've seen and as the students have shared, they expect the transition state for pathway 2 to be higher in energy. So if we have pathway 1, so here's pathway 1, and our transition state looks like this. Does everyone remember what this transition state, where we're forming a bond with our nucleophile, breaking a bond with our leaving group? Does this transition state look familiar to everyone? Okay, perfect. So we know for pathway 2, which has, so pathway 1 is our primary substrate. And so we'd expect the transition state for pathway 1 to be lower in energy than the transition state energy for pathway 2. The reason for that is that in pathway 2, we have additional substitution. We have another methyl group, and that increases the steric bulk and steric repulsions. Okay, so now thinking about our reactants, there's not going to be an appreciable difference in the reactant energy for the most part, or at least it's not going to make a difference when it comes to the final outcome of our reaction. So we see we have a very large activation pathway, or activation energy for pathway 2. For pathway 1, whoops, let me use a different, there we go. So we see that for pathway 1, the activation energy is lower for pathway 1. Does that make sense to everyone? Does this idea make sense? And does how to present this material using these reaction coordinates make sense? Break it up into pieces. And once you have each of the pieces sorted in terms of energy, then all you have to do is connect each of the parts with a line. So in summary, the more hindered our substrate, the slower the rate of reaction. The reason for that is the more steric hindrance we have, the higher energy our transition state is, the harder it is for us to access our transition state, and the lower the rate of reaction. Does that make sense to everyone? Okay, so let's keep going now. And let's talk a little bit about some applications. Let's talk a little bit about some applications for explaining and rationalizing reactions. So I'd like us to draw a mechanism for the following reaction and predict the products from each reaction. As a bonus, we're going to draw and we're going to try to predict which chair conformation is more reactive. So, taking a look at this substrate, let's try to take about 3 minutes and let's try to draw the product from this reaction. Let's try to draw an arrow pushing mechanism for this reaction. And most importantly, I'd like you to tell me the product stereochemistry. Because remember, SN2 reactions care about stereochemistry. So let's take a moment for about 3 minutes, and I'd like someone to share their proposed mechanism using the annotate tool. And in the meantime, I'm putting together a model of this structure, and that's probably a sign that you may want to use a model kit for this problem. But let's see some shared mechanisms, and then we'll discuss this example in about 3 minutes. Would anyone like to share a proposed mechanism for this SN2 reaction? Don't be shy to break out the annotate tool and share your proposed response. So we have a student typing in the chat. They think the nucleophilic carbon will attack from beneath on the opposite side, and the iodine will be pushed out. Okay. Now, I'd just like you to tell me then, I'd just like you to tell me then, should I draw my bond to cyanide with a dash or a wedge? How should I draw this bond if I'm respecting the stereochemical outcome of this reaction? So we have a student proposing it should be drawn with a dash. What does the rest of the class think? Would anyone like to share their responses as well? Would anyone like to share their proposed responses as well? So let's look at a model for this structure and let's talk through and let's try to explain and rationalize this reaction. Okay, so in a typical SN2 manner, it occurs as a concerted mechanism where our nucleophile attacks our carbon and our leaving group leaves. Taking a look at our substrate, taking a look at our starting material, for our iodine atom, should it be assigned a dash or a wedge? In this initial starting material, the iodine is pointing up out of the page, so it should be assigned a wedge. Cyanide attacks opposite to our leaving group, and the SN2 reaction occurs with inversion. So that's why we end up with a dash. This would look like practically, if our cyanide has a dash, it would look like this. Now, in terms of which chair conformation is more reactive, let's take a look at both of these chair conformations. Since remember, and this is an important point that we need to start to think about, both chair conformations are accessible. So let's think for a moment about which chair conformation is actually more reactive for this SN2 reaction. So we have our two chair conformations drawn. Okay, so in terms of approach, let me show you a model kit with all of the hydrogens added and included in our structure. And this is really informative to think about because it helps you start to one, appreciate the fact that chair conformations are really important in terms of figuring out which conformation is most reactive. And two, it can help explain why in some cases, certain substrates react incredibly slowly via the SN2 mechanism. Okay, so let's take a look at okay, so let me share the camera and let's take a look. Okay, can everyone see the structure? Can everyone see the camera? Okay, so now taking a look at this structure, does everyone see our iodine pointing up? Does everyone see our iodine pointing up? Okay, so our nucleophile needs to attack opposite to our leaving group. Okay. Now, looking at this from the perspective of accessibility, is it easy for my nucleophile to slip in here? Is there anything blocking my path? So just like if I physically move my nucleophile and I try to push it behind my leaving group, is there anything blocking my path? No, so it's pretty easy. We have a nice straight shot to attack. So nothing really giving us any trouble there. Okay, now let's do a ring flip. Okay, and now we're in for a bit of a annoyance here. Now we're in for a bit of an annoyance here. So here's the ring flipped structure. Okay, does everyone see how the iodine is now equatorial? Okay, now I'd like you to think, if I want to attack from the back side of my leaving group, I have to go like this, right? Now, does anyone notice something getting in the way? What's getting in the way of my approach? Do I have some hydrogens blocking my approach? Yes. So if we try to draw a straight shot approach of our nucleophile, so if we try to draw a straight shot approach of our nucleophile, the hydrogens block the approach. I mean, hydrogen isn't enough to stop the approach, but it certainly makes it harder. So then, comparatively, which of these two conformations is more reactive? Conformation 1 or 2? Which conformation is more reactive? 1, exactly. Now, when can this be a problem? If your molecule is locked in a non-reactive conformation, you can sometimes see a really slow SN2 reaction for no other reason than your substrate is stuck in a very unreactive conformation. So in this case, only one of our conformations is more reactive, and interestingly, it happens to be the higher energy conformation. So it's important to not only think what's going on mechanistically, but also when I look at my chair conformations, can I access this conformation, and which conformation is needed for reaction and which conformation is favored for reaction. In this case, they can interconvert pretty readily, but that's not always the case, as we've seen. Does this example make sense to everyone? Perfect. So let's keep going now. And I'd like you to predict the products from this reaction, and I'd like you to draw the reactant and product in dash wedge notation to justify your answer. So this is the type of thing that you'd see on your exams. So I would recommend attempting this. So let's work on this example. We'll take about 4 minutes to work through this example. I'd like you to share your proposed structures using the annotate tool, and then I'd like you to draw a mechanism for this reaction. And don't worry, this training does have a purpose. There's a payoff to this process that I'm using here, because you'll apply this same logic when we talk about other types of substitution and elimination reactions. So first things first, I'd like to see a dash wedge notation structure. I'd like to see a mechanism and then the products. And one trick to make predicting the products with the model kit easier is I like to use if you have in your model kit a carbon with 5 pegs, that is really useful for this, because what you can do is you can just slot in your nucleophile and just detach the leaving group. We'll show that in a moment. So let's focus on getting a dash wedge notation structure for the following molecule. And then we'll discuss this example in about another 2 to 3 minutes. But I'd like to see some proposed responses using the annotate tool, or you can even attach a photo, or you can ask a question, or you can share your responses verbally. Either method would work. Would anyone like to share a dash wedge notation for this structure? And don't be shy to share your responses using the annotate tool or in the chat. And we'll discuss this example in about another 2 minutes. I'd like to see some shared responses just to make sure everyone's following along, or even a question. Okay. So let me draw out what the student mentioned. So on the left, I have a like this. Is this the student proposed structure? Okay. So let's talk through this. So first, there are 2 methods you can use. We could use the dividing line method. So I draw a circle. So anything on the left of the line gets a wedge. Anything on the right gets a dash. So let's see how the student response compares to this method. So first on the left, so our bromine is going to get a wedge, and our methyl group will get a dash. Okay. The methyl group gets a wedge, and the hydrogen gets a dash. Oh, okay, perfect. I was wondering about that. Okay, so this is the structure that we get using the dividing line method. Let's also try this with the camera method. Okay, so here's our structure. Now, in order to go from the Newman projection, to dash wedge notation, all I'm going to do is I'm going to turn this structure on its side, and I'm going to make my carbons as part of the central carbon chain. And now all I'm going to do is I'm going to draw what I see. So this structure is equivalent to the following. So we have our carbon chain, and which groups are pointing towards us? Hydrogen and bromine, right? Yeah, this is fine. There are many ways to rotate your molecule. Okay, and then we have the hydrogen and hydrogen pointing away from us. This back center isn't a genuine stereocenter. Okay, so now in the SN2 reaction, our nucleophile is going to attack from the opposite face. So if here's our molecule, our nucleophile, which in this case is acetate, is going to attack from the opposite face, and we're going to see inversion of our stereocenter. So my acetate is going to attack from the opposite face, and we're going to kick out our leaving group. Okay, so then, now that we have that drawn, so as we have inverted this stereocenter, initially the center is R. Now at the end of this process, my question to you is, what group is now in front? What group is now in front pointing towards us? What is now in front after this displacement? The hydrogen. Let me tilt it a little bit. There we go. So which groups are in front? Oh, both hydrogens, yep. While our acetate is in back. And as we notice now, this center is now S. Does that make sense to everyone? Does everyone see how this displacement occurred? Let's look at it from the Newman projection perspective, since that's sometimes also easier to see. Okay, so here's our initial Newman projection. Let me get things right so that way we can see it. Okay, so here's our initial Newman projection. And in this case, acetate is going to attack opposite to our leaving group. And we're going to kick out bromine. So when that happens, we would end up with the following structure. And in turn, that would look something like this. Okay. Okay, so now that we've set that up, we can convert this structure into dash wedge notation just via rotation. So let's show what this would look like after rotation. So we rotate this structure and we set it up. So both of our carbon chain, all of our carbons are part of the main chain. And as we notice, do we get the same result with both of our hydrogens in front? Yes, perfect. So your final response would be this. And I would recommend, and I would highly recommend assigning your stereochemistry for your products to make sure that you actually inverted your stereocenter. Does that make sense to everyone? So this is a good stopping point for today. So we'll take a quick 10-minute break and then resume for laboratory.